There's another application which is much more mathematical in nature. I'd like you to find the values that a parameter or parameters have to take so that a linear system has either no solution, a unique solution, or infinitely many solutions. So if we look at the system kx plus y plus z equals 1, x plus ky plus z equals 1, and x plus y plus kz equals 1. The parameter in question is k. There's only one in this example. Like tell me what the possible values of k are in each of the three typical linear system scenarios. So we test for parameter values in each of the scenarios. Now this system is linear in the variables x, y, z. If you treat k as a variable as opposed to a parameter, it is not a linear system anymore, because then you'd have products here. K and x would be product. But if you treat k as a parameter, it is a linear system. You're saying, I don't know what the value of k is. All I know is it has to be a real number and it's fixed. Like once I pick a k, this is my system. So what are the options? Well, you would then start by putting this system into its augmented matrix. And you would go and try to row reduce the matrix to see what you can get to from the given coefficient and constant term. Coefficient matrix and constant term. If you have a unique solution, you should be able to bring it down to the identity matrix here and the coefficient part, and then the solution will be what shows up on the right of the vertical line. If you end up with no solution, you'll end up with a row of zeros and something which is not zero here, at least one of them. So you'll have a degenerate, inconsistent row. And if you end up with infinitely many solutions, you'll have the rank of the augmented matrix being equal to the rank of just the coefficient matrix. And we're expecting this rank to be smaller than 3 in this case. The problem right off the bat is that you can't divide rows by k because you don't know if k is equal to 0 or not, right? If you try to divide row 1 by k, the idea would be to have k over k and that's 1, then you'd have 1 over k, 1 over k, 1 over k. But you can only do that if k is not equal to 0, and you don't know what the value of k is. So as you go through the process, you will end up identifying branches of the scenario. You could start by saying, let's assume that k is equal to 0 and take it from there. Or you can say, let's say k is not equal to 0, and then you divide by k and you take it from there. It is not obvious what the best way to approach this would be, but one of the things you could do is actually to start by swapping row 1 and row 2 together. So now you don't have a k to transform in the first position of the first row anymore. You already have your leading 1k, 1, 1, which comes from the second row, the original augmented matrix. Okay, so we do the swap and we get this matrix right here. So now we come up with 2 additional elementary row operations which will create zeros underneath the leading 1. As we want to create a 0 in the second row, we'll have to have something like row 2 plus blah 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 into row 2, and the blah 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 has to be some scalar multiple of what? Of row 1, because that's the leading 1, the pivot that we're using to create these zeros. Like, okay, well, what do I have? I would have row 2, which is k, plus a times whatever my row 1 would be, so a times 1. I would like this to give me 0. So I don't know what a is going to be here. That's what I'm trying to figure out. It gives me an a, which is minus k. So what that tells me is that row 2 minus k times row 1 into row 2 will create a 0 here. Now I apply this elementary row operation to the entirety of row 2 and row 1 together. So what happens to the second term here? Second term would be 1 minus k times row 1. So 1 minus k times k gives me 1 minus k squared. Then I have 1 minus k times 1. That's 1 minus k. And finally 1 minus k times 1. Again 1 minus k. Alright, so this is the second row. And the elementary row operation we use to create a 0 in the third row underneath the pivot in the first column would simply be row 3 minus row 1 into row 3. Again, we need to put something into row 3, so row 3 has to show up here alone and together with some scalar multiple of row 1 because we're pivoting using the leading one of row 1, and then we'll find it's not difficult. If I want row 3 minus something times row 1, which gives me 0, I don't have a choice, it's got to be minus 1. So row 3 minus row 1 into row 3 indeed gives me 0, and then I end up with, for the second column, 1 minus k, which is here. Then I have k minus 1, and finally 1 minus 1, which is 0. Okay, so I've simplified this. I've created the first bit of my row echelon form. Then I need to know what I'm going to do for the next little bit, and I have no choice, right? You got variables in both of your entries from which one of these has to be a leading one, so I can't just go and swap rows anymore. I'm going to have to consider the possibilities. If k is equal to 1, then all of the terms that are here end up giving you 0. So if k is equal to 1, the augmented matrix reduces to this augmented matrix, which is a consistent augmented matrix. It has 2 non-leading variables, so it has infinitely many solutions. At the very least, the scenario where you have infinitely many solutions has to include the case k equals 1. If k is not equal to 1, then 1 minus k is different from 0. And then you see here why we bothered specifying 2 possible cases for k, equal to 1 and then not equal to 1, because we were going to try to create a 0 for this thing here. So if 1 minus k is different from 0, we can divide rows by 1 minus k. And I'm going to do that. I'm going to divide both row 2 and row 3 by 1 minus k. So if I do 1 over 1 minus k times row 2 into row 2, what do I get? Well, I had originally in this position for row 2 1 minus k squared. I remember that this is 1 minus k over 1 plus k. And if I divide that by 1 minus k, assuming of course that k is different from 1, then these 2 terms cancel out and you're left with 1 plus k. Great. Not quite a 0 yet, but we're getting there. And then we have 1 over 1 minus k times whatever the entry here was. It was 1 minus k, so that gives me 1. Similarly for the other term. So the second row clearly becomes 0, 1 plus k, 1, and 1. And I do the same thing for the third row. And I get 0, 1, minus 1, 0. And at that point, I have something which is clearly a 1 that I can swap and place into the right position by just swapping row 2 and row 3. So this is eventually going to be my leading one, and this is going to be a 0. That's my plan. I want to end up with something that looks like this. So I have to transform this into a 0. The suggested elementary row operation is row 3 minus 1 plus k row 2 into row 3. So you conduct that operation on this matrix here, and you will obtain the following echelon part. Okay, so right away I can tell when the system is going to be inconsistent. I'll need to have that k is equal to minus 2. Because if k is equal to minus 2, then this is 0, and this is 1, and that's a degenerate, inconsistent row. One thing you have to ask yourself is, well, does it make sense for k to be equal to minus 2? Well, we are in a specific case. We're in the case where k is not equal to 1. And sure enough, if k is not equal to 1, k could, in theory, be equal to minus 2. If you're not in that case, if k is not equal to minus 2, then you could divide this row here by 2 plus k, and you would get a 1 here, and then you would get 1 over 2 plus k. And that would be a pivot. You'd have a rank of 3. You have a unique solution, you're happy. So if k is equal to 1, there are infinitely many solutions. If k is equal to minus 2, there's no solution. And if k is neither 1 nor minus 2, then there's a unique solution. You have to be familiar with this kind of procedure.